Okay, yeah, so I'd like to start by thanking the organizers for giving me the opportunity to speak at this conference organized in honor of Deepak. I'll be talking about activity-driven transport in harmonic chains. So this is based on these two works done jointly with Ayan Chhatra, who is here, and Ritik Sarkar, who is my PhD student. So this is the brief outline of this talk. First, I'll give a very brief recap of energy transport in thermally driven harmonic chains. And then I'll go over to active reservoirs and give a very simple model of active forces, how we drive with activity. And then I'll talk about the transfer properties, particularly average energy current, temperature profile, and fluctuations. Okay, so so when we talk about or think about energy transport in macroscopic systems, the picture we have in mind is a system which is attached to two different temperature baths, like the cartoon you saw in Anupam's talk earlier this morning. So these are two different temperatures, and then there is some heat or energy flowing through the system. So often, theoretically, these are modeled by, the system is modeled by oscillator chains, again, like you saw in Anupam's talk this morning. And the boundary oscillators are connected to thermal reservoirs with different temperatures. And when the temperatures are different, there's energy current flowing. So the questions that are usually asked is, what is the amount of the energy current flowing? How is the thermal conductivity behaving? Is there a Fourier law? What is the local temperature, and how does the velocity or local position fluctuate? Okay. So the first paradigmatic example in 1D was considered by Ryder, Lebowitz, and Leib long back in 1967, where they modeled, used a model of harmonic chain. So these are just harmonic oscillators connected to nearest neighbors, and the boundary oscillators are connected to some thermal reservoirs. I'll talk a bit more about what are these reservoirs. So here, let me define it in some more details. So we have a chain of n oscillators. So these blue particles are oscillators, and they are connected to the neighbors with harmonic interaction. So they are moving about, and the displacement from the equilibrium position is denoted by XL for the Lth oscillator. And then the boundary ones, the first and nth oscillator, are connected to two different temperature reservoirs. And these reservoirs exert certain forces on the boundary oscillator. So there are usually two components of this force. One is just the random force, the thermal noise, and then the oscillator also loses some energy, which is characterized by this dissipation. Because we assume that these reservoirs are in equilibrium, so that means that the noise and dissipation have to be connected. They cannot be independent of each other. So fluctuation dissipation theorem is what connects this noise and dissipation. Okay, so there are various different models of oscillators possible. All must satisfy FDT as long as we are talking about equilibrium and thermal reservoirs. So the simplest model perhaps is the so-called Langevin bath, where the noise is just a white noise and the dissipation is constant. Okay, so here are the Langevin equations describing the motion of these L oscillators. So each oscillator is connected to two neighboring ones. So XL has a force which depends on XL minus 1 and XL plus 1. And apart from the boundary ones, there are no other noises. On the boundary ones, there are these, four different forces. And as I said, FDT says that the strength of the noise has to be proportional to the dissipation, and the proportionality constant, the square root of dissipation and the temperature. Okay, and this model was studied in details in 1967, and also many different aspects later. So let me give a brief summary of what happens here. So because the model is linear and the noise is Gaussian, so it allows exact solution. So one can compute the exact current flowing through the system in thermodynamic limit. And as it turns out that this current is simply proportional to the temperature difference. So we have two temperatures, T1 and T2 at the two ends. And the current is simply proportional to this difference. And it also depends on the other parameters like the mass of the oscillators and the dissipation and the strength of the coupling. Moreover, what happens is that if we look at the local temperature of the oscillators, then in the bulk, it's simply uniform and it's given by the average of the two temperatures. So a natural question is what happens when these reservoirs are away from equilibrium? So if the FDT is not satisfied, and in particular, the question that I'm going to ask is what happens if these reservoirs are active? So what I mean by active reservoirs also was what was discussed by Sriram earlier in his talk. So we are talking about a medium of, which consists of self-propelled active particles. like bacteria or genus particles, which have certain time scales in their intrinsic dynamics, which makes them non-equilibrium inherently. And so when we are talking about a collection of such particles, that's what I mean by an active reservoir. So recently, the motion of single probe particles in such active reservoirs have been studied a lot. And it was shown that many intriguing features actually emerge, like modification of equipartition theorem and negative friction can come out of this, probe motion in such an active medium. So here are some references. There are many more, of course. So the question we are going to ask is, we are not talking about a single probe particle, but an extended system, and we connect it to two different active reservoirs. So the activities will be different, and we expect some sort of energy current then flowing through the system. And we are going to ask how this current behaves and how is it different than the thermally driven scenario. Okay, so again, we'll take a very simple linear model. So that's what I call, that's what I call activity driven harmonic chain. So here again is the model. We have the same setup. We have n oscillator chains connected to neighbors through harmonic interaction, and also thermal reservoirs, the usual thermal reservoirs. But additionally, now we consider two extra forces on the boundary oscillators, which are what I call active forces. They have some memory. Okay, and then so these forces do not satisfy FDT. So the dissipation and these forces are not related, which makes them which makes the reservoirs now non-equilibrium. Okay, so here is the Langevin equation. So we have exactly what we had before, except these extra forces on the boundary oscillators. So the thermal part satisfies FDT. Here is an extra force which does not satisfy FDT. So in total, the reservoirs are out of equilibrium. And so yeah, so this FT I call active force. And what I assume for the moment is, so these are unlike the white noise, these are correlated in time. These have some memory. And again, for simplicity, I take this very simple exponential correlation. So the FT prime decay exponentially. So J is the index of the reservoir. So we have one time scale tau1 for the left reservoir, and then another time scale tau n for the right reservoir. So these time scales are my measure of reservoir activity. And we expect already that when this tau goes to 0, so that's some sort of passive limit. So there, this exponential correlation function actually becomes delta correlated, and we expect some sort of effective thermal behavior in that limit. I'll come back to that in a minute. So now the question is how exactly we model dynamically these forces. So I have assumed that they have exponential correlation, but one can get exponential correlations in many different ways. So here are the three cases that I'll consider. So these are the usual active processes, the so-called Run-on-Tumble process, active Brownian process, and active Ornstein-Uhlenbeck process. This again Sridhar mentioned in his talk. Here are the two other things. So Run-on-Tumble process is basically where the force can have two different values, capital A and minus capital A. And then there's a sigma, which is a dichotomous variable. So it can just flip sign with rate, some rate alpha j. And if you, so here is the propagator of this process. And if you compute the 2-point correlation of this F, then you actually get this exponential correlation with the activity tau, which is basically given by 1/2 alpha. So 1/2 alpha is the rate of this flipping. So that is one process by which you can get such an exponentially correlated active force. Another is the active Brownian process, where this force is derived from some angle. I mean, you can think of it as some internal angle of some particle, and that undergoes a diffusion. And again, you get an exponentially correlated, exponential correlation with the activity now given by the inverse of the diffusion coefficient. Okay, and then there's the Ornstein-Uhlenbeck process, which we saw. And this process is completely Gaussian. So the propagator is completely Gaussian. So you don't need to remember the processes exactly, but the point is that these are very different dynamical processes. The propagators are very different, but all of them have exponential correlation. Okay, and we'll see that that actually suffices to a great extent. Okay, so the question that that I'm going to, this is the time remaining, or okay. So here are the objectives of this talk. So we are going to, look at the stationary state, which arises out of this active drive, and in particular the average energy current, temperature profile, and if time permits, velocity and current fluctuations. And okay. So again, we have a very, it's a linear system. So one can actually exactly compute all these quantities. So we use the Fourier transform and Green's function method, which was introduced by Abhishek in 2001. And the displacement of the electric particle can be written in this form. Again, you don't need to remember the exact form, just that it is linear in noise. With a Green's function matrix, which is inverse of a tridiagonal matrix, which allows for exact computations. Just one thing. So here, this xi tilde and f tilde are the Fourier transforms of the white noise, the thermal noise, and this is the active component. Okay. So the difference between these two is that the white noise has a spectrum which does not depend on the frequency. Okay. So it's uniform, only delta omega plus omega prime. In contrast, this active force, because we are taking it exponentially correlated, so it has a spectrum which depends on tau, and this spectrum is actually Lorentzian with width, which depends on the activity of the reservoir. Of course, this does not depend on the specific dynamics as long as it's exponentially correlated. Higher order correlations of this force, of course, would depend on specific active processes, but that does not concern us yet. Okay, so we compute first the energy current, which is the average energy flowing from the reservoir to the first oscillator and then from first to second. Because there are no sources of dissipation in the bulk, so the average current flowing through the system is constant. It doesn't depend on the oscillator that we are looking at. And again, because of the linearity, it turns out that the total current just separates out into two components. One is the thermal current and the other one is the active current. So the thermal current is exactly same as what we saw earlier, what RLL got in their model. Proportional to the temperature difference. So, we don't bother about it so much. I'll just put, we'll assume that the temperatures are 0 and concentrate only on the active current part. Okay. This can be computed. So here is a Landauer-like formula which gives this current in terms of the active spectrum and the transmission coefficient. So here, this is the transmission coefficient of the linear chain. It doesn't depend on the driving or anything, just the system parameters, the coupling constant and the mass and dissipation. And here is the reservoir spectra. It's actually the difference of the reservoir spectra of the two reservoirs. And again, as I've been pointing out, it's independent of the specific dynamics. As long as it's exponentially correlated, we are fine. Okay. So this presence of this Lorentzian spectra actually changes the behavior of the current quite drastically compared to the thermal case. And in the thermodynamic limit, where contributions come only from the system phonon band, we can calculate this current exactly. So this is the form. This is how it depends on tau. Again, you don't need to remember the exact expression, but some complicated form just to show that we can calculate it exactly. But this has certain very intriguing features. So here is a plot of the total current as a function of tau1, the activity of the left reservoir, for different values of the activity of the right reservoir. Okay, so you can already see there are two intriguing features. One is that the current is a non-monotonic function of tau. Okay, so fixing tau n, changing tau1, that's like changing the activity drive. So when we increase the drive, the current first increases and then decreases again. So this is something we never see in equilibrium, right? So for thermal driving, we can never see a non-monotonic behavior like that. So this is what is called negative differential conductivity. So if we take the local derivative, that's like the differential conductivity dj d tau, that is negative at in some regime of tau. And moreover, we see that if we keep on increasing it, the current actually changes sign. So here, if we follow this blue curve, let's say, so the current starts from some negative value. It crosses 0 when the activity of the two reservoirs are same, when tau1 equal to tau n, somewhere here. And then it goes up, goes down again, and then it becomes negative again. So here, at this point, there is a finite drive. The drive did not change direction, but the current changes direction. So that is kind of surprising. And this is a clear signature of activity of the system. Okay, here, the symbols are simulations with RTP driven case. But again, it doesn't matter what specific process we take, any at least, I mean, as long as the strength of the noise is independent of tau, which is for RTP and ABP, then we get the same situation. Temperatures, I'm assuming that that's 0. So the current completely separated out. So I'm talking about only the active component of the current. Okay. So this negative differential conductivity is a counterintuitive phenomenon, as you can imagine. I mean, we are increasing the drive and the current is suddenly starting to decrease. But there are certain examples of this NDC in non-equilibrium systems, like in rotor chains or in presence of obstacles or in the presence of kinetic constants. But here, I mean, these are all nonlinear systems. But here, this activity drive leads to NDC in a very, very linear and exactly solvable system. So the question is, what is the origin or how to understand this? So one way to understand is to look at the spectra again. You remember we had this Landauer-like formula where the current is given by the sort of the overlap of the difference of the two reservoir spectra with the system transmission coefficient. So this transmission coefficient here, this blue curve shows the transmission coefficient of the harmonic chain, which has two peaks near the characteristic frequency, this 2 square root k by m. And the system spectrum is a Lorentzian, which has a peak near omega equal to 0. And the current is actually given by the overlap of these two functions. So here, this is shown for different values of tau. I mean, we are now talking about one of these things. If we can understand the non-monotonicity in one of them, then we know, I mean, we can have it for both of them. Okay, so here you see that if I increase tau, so the blue curve is tau equal to 0.1, then this is tau 0.5, and then tau equal to 5. So the overlap actually changes non-monotonically, which in turn results in the change in the area, which gives rise to the non-monotonic behavior of the current. There is another way to understand this NDC, which is through the perspective of non-equilibrium response theory, but I'll not go into that in this talk. Instead, let's look at the current reversal a bit more closely. So here is a plot on the tau 1, tau n plane, where I'm just showing you, I mean, where the current is positive and negative. So this is the line tau 1 equal to tau n, and you would expect the current sign to change when we cross this line because the direction of the drive is changing. But here is another line, this red line, which is non-trivial. So some tau n star, which is a function of tau 1. And when we cross this line, we also have the additional current reversal. So if I follow this red line, which is for a fixed tau n, so like here, so we start from the negative current and then it becomes positive and negative again. So here from this plot, so this is the active current in the 3-dimensional plane. So here, from here, you can see that there is a special point, this I mean, on this tau 1 equal to tau n line, which is a saddle point, which I'm calling tau bar. So if we pass through this line, either this way or that way, then there is no current reversal. So this way, the minimum value of current is 0. That way, the maximum value of current is 0, but there is no reversal if you pass through that point. Okay, so the next question is, what about the temperature profile? So for thermally driven case, we saw that the average temperature is actually uniform. It's just the average of the two, I mean, temperature of the two reservoirs. So what about here? So here we can also define kinetic temperature as the average kinetic energy of the Lth oscillator. And also because of the harmonic coupling, we can define something called a potential temperature from average potential energy of the oscillators. Okay, and again we can calculate it exactly. And it turns out that in the thermodynamic limit, in the bulk of the system, these two are same. So there is some sort of an equipartition of energy. The kinetic temperature and the potential temperature are same in the bulk. Although near the boundary, they show different behavior. But moreover, this bulk temperature actually is given by is of this form. So half of some quantity, which I'm calling curly t, T1 plus Tn, where this T1 depends only on tau 1 of the left reservoir parameters and Tn on the right reservoir parameters. So this is very similar to the thermally driven scenario, right? If we could call this curly T1 and Tn as some effective temperatures of these active reservoirs, then we can actually define, I mean, understand this as thermally driven scenario with some different temperatures. Okay, so the next question is it true? Can we actually do that? So the answer is no, because there are certain significant dissimilarities with the thermally driven scenario, despite the uniform value at the bulk. So one thing is that if you look here, so this orange curve, this is for tau 1 equal to tau n equal to 1. And in that case, in the thermally driven case scenario, you see just a uniform profile, no boundary layer at all. Okay, here you can see that there is actually a non-trivial boundary layer even when tau 1 equal to tau n. So this is the first dissimilarity. Another one is that for thermally driven case, we always see some sort of a kink at the boundary, except when T1 equal to Tn. This is also absent here. We just have an exponential boundary layer, no kinks. And then finally, so now suppose, I mean, we assume that, okay, these are the effective temperatures. Now I can ask the question that, I mean, given these effective temperatures, what is the current? Is it same as the one we can get from the thermally driven scenario? So we just put these effective temperatures in the formula computed by Ryder-Levin-Lebovic. And here we are comparing the actual current with that. So the dashed line is the current expected from these effective temperatures. And the solid lines are the actual currents that we get from the exact computation. And you see that these don't match except here in this brown curve. So here is a special situation where it is matching for small tau 1 and tau n is also very small. Okay, so this is the so-called passive limit. But in general, no effective temperature picture can be built. Okay, so now let's try to understand this passive limit, which occurs when the activities of the reservoirs are small. Okay. So in this case, the correlation, the exponential correlation actually reduces to a delta correlation with some effective strength, and that gives the effective temperature of the reservoirs. And we can show quite easily from the exact expression that we have that if we take this limit, that reduces to the already known result. So in this small activity limit, it's a passive limit. We have some effective temperature picture, and yeah, and that's it. So here, let me summarize up to this. So we are studying energy transport of harmonic chain connected to active reservoirs. Very simple model of active reservoir, just some active forces with a memory, I mean a time scale, and we could calculate the energy current and temperature profile. And we saw that the energy current, I mean, despite the simplicity of the model, the energy current shows certain weird features as NDC and current reversal, and these are quite robust. As long as we have this exponential correlation, the form of the current actually remains same. Okay. So the next question is, how do we see the signature of the active force? I mean, the actual force I'm using. There is a dynamics which is giving rise to this exponential correlation. But as we saw, the actual propagators of these three different processes are very different. So how do I see the signature of that? So what we thought is that maybe in higher orders, we should see the effect of this. So we looked at local velocity fluctuations and local instantaneous current fluctuations. Okay, so here are the plots. So here on the left panel, what you see is the velocity distribution of the middle oscillator, but it doesn't matter if you take the middle one, any oscillator in the bulk would give you the same result, and it's actually completely Gaussian. Okay, so in the bulk, at least velocity fluctuations, we don't see any signature of activity except through this through the width of the distribution, but it's Gaussian like in the thermal case. Okay, so this is, I mean, one possibility is ruled out. From the velocity distributions, we cannot distinguish between what kind of driving we are using. I mean, what specific dynamics we are using for the active force. On the other hand, if we look at the boundary velocity distribution, then of course, I mean, we'd expect some signatures, and there it is. So the green curve is the boundary velocity distribution for RTP driven case, and these two are AOUP and ABP. So the green curve, I mean, RTP and ABP are not Gaussian. AOUP, of course, has to be Gaussian. The process itself is Gaussian. But in the bulk, we don't see any signature of the specific drive. Okay, next is when we look at the distribution of the instantaneous local current. Okay, so here is the current. So we have average velocity of the two oscillators. So we are looking at the current flowing through the bond between L-1 and Lth oscillator. So this is the definition. And of course, without knowing the stationary state measure, we cannot calculate it exactly. But what we did, sort of, drawing inspiration from this plot. So if the velocity distribution is really Gaussian in bulk, So we assume that the velocity and position distributions are actually Gaussian, and then we can compute this distribution exactly. So this is the form. It involves Bessel function. This of course is exact for AOUP, where the measure is actually Gaussian, but for RTP and ABP we don't have any proof that this is Gaussian, but it looks like Gaussian in the simulation. And so we calculated anyway the local current distribution, and surprisingly here, I mean, we saw that it actually matches the current distribution. So here is a plot of the current distribution for a fixed tau n and different values of tau 1. So, and the black lines are the distribution calculated using this Gaussian assumption, and you see that they match quite well. Okay. So one feature here is that the current distribution has a peak at 0, even though the average is non-zero in two of these cases. In one case, it's the average is 0, and of course this ABP and RTP are actually, I mean, if you scale it properly, they collapse, and the collapse curve match quite well with this I mean predicted current distribution from the Gaussian calculation. Okay, so somehow the system becomes, I mean, the non-equilibrium stationary state, irrespective of, I mean, despite being driven by some force with memory, the bulk oscillators are showing completely Gaussian behavior in the stationary state. And okay, so now we also looked at, I mean, looked a bit closely to see whether it's really matching. So here, this is a plot where we show the behavior near origin. So from the calculation, we expect a log divergence. Okay, so here are two sets of curves, one for RTP and the other for ABP. And in both cases, we see that the log divergence is actually matching extremely well near the origin. So, okay, I mean, again, more evidence towards Gaussianity in the bulk. And then there is an asymmetric exponential decay at the tail. It has to be asymmetric because, I mean, we have an average current. There is an average current flowing through the system. So the distribution of current cannot be symmetric. So, I mean, here are the expressions, and these also match quite well. As you can see from here, this is a semi-log plot. So the tails are also matching quite well. So probably there are some signatures of the specific driving near, I mean, for large deviations. But as far as the typical fluctuations go, it seems like the system doesn't know exactly what kind of drive we are using. As long as it's exponentially correlated, everything is Gaussian. The current has a weird behavior, but apart from that, there is no specific signature of activity except through the width, of course, that depends on tau. Okay, so what about the current fluctuations at the boundary? So far I've been talking about the bulk current. So if we now look at the boundary current, that we expect to have clear signatures of activity in. So we have the active force here directly, and it turns out that yes, it does. So for AOUP, of course, again, everything is Gaussian. There is no problem. It's exactly same as what we expect. For RTP and ABP, however, the boundary current distributions are very, very, very different. So here, so in both cases, first of all, there's an upper bound, which comes from the fact that this F is bounded. So it can take only, I mean, the value of F can be only in a certain range. It cannot be unbounded, and that gives rise to a bound in the boundary current itself. And this bound we could calculate for both cases, for ABP and RTP. But as far as the nature of the distribution goes, we don't know what exactly it is, but it looks, so remember again that one of these curves in both cases, the green one actually has average 0. Okay, so there is no average current flowing through the system, but the distribution still looks like that. Okay. So yeah, I am done with about 5 minutes left. So, so we are looking at non-equilibrium stationary state of a harmonic chain driven by exponentially correlated active force, and we looked at transport properties and which showed certain interesting behavior. But even more interesting or more boring, depending on how you want to think about it. So there are certain universal bulk properties. Local velocity and current distributions are consistent with Gaussian stationary state. However, at the boundary, we can see signatures of specific active dynamics. So there are, of course, many open questions now. So first thing is that we took a very simple model of the active reservoirs, just some force with an exponential correlation. But what happens when we have a more realistic model of the reservoirs? In particular, if we include the dissipation, which comes from an active reservoir, which would be very different than a constant one. So what happens? Do these current reversal, etc., survive? Okay. And then another question is, again, how does it change when we add some disorder or anharmonicity in the system? So our preliminary simulations suggest that actually effect of anharmonicity does not destroy this current reversal or non-monotonic behavior. It is there. Of course, in that case, we cannot do any exact calculations, but at least a numerical simulation suggests that it's still there. Yeah, so with that, I again like to congratulate Deepak for his honor, and thank you all for your attention.
Questions, comments? Please wait for the mic so people online can hear us.
This non-monotonic behavior, why is it interesting? The non-monotonic behavior of the current?
So this is very counterintuitive, right? So you are pushing something.
Okay.
You are pushing, and the velocity of the thing is first increasing and then decreasing, right? So it's like getting less by pushing more in some sense.
Okay. I was just wondering whether it has some biological advantage or
biological advantage, possibly yes.
Okay.
Depending on the scenario. Yeah, so in some optical systems, they call it so optimum drive, so where it becomes maximum. So then, I mean, you can tune your parameters where it is maximum and operate at that. As far as biological advantage go, I mean, I don't know any specific examples, but you can imagine, yes, I guess.
No questions.
Can I ask a question? Can you hear me? This is Joachim Krug. Hi.
Yeah, go ahead. Go ahead.
Yeah. So I think you already said this in some sense at the end, but just to clarify, so you're basically just looking at correlated reservoirs, right? So they are not specifically active in the sense that there is some sort of time reversal symmetry breaking in the reservoirs. Is that correct?
Yeah. So for the moment, we are taking just a force. And the force dynamics is the usual active particle dynamics. So that's why I'm calling it active reservoir, but you are correct. I mean, a more accurate way would be to describe, I mean, a more accurate way of describing would be to consider the boundary particles as the active particles themselves.
Okay, thank you.
I guess two questions. First, what would happen if you took the active particles to have not to be mean zero in time?
Okay.
So like it's as if I'm thinking of the article by Marielle Simon, Tomasz Komorowski, and Stefan.
So you want them to have a drift?
Yeah, it's like because one of the examples I think you cited as like where they had an uphill diffusion, or sorry, NDC is like when they would have like a harmonic chain with spin flip, but then they'd be pulling on it as well.
No, I didn't get your question. Can you repeat it? So you have a harmonic chain.
Yes.
And?
Well, when they had their example of like a non-linear temperature profile with a harmonic chain that came out of the fact that they were also pulling on the chain as well from one side.
Oh, yes. Okay. So they were pulling it from one end, right?
Yeah.
With a constant force. But these are not harmonic oscillators. These are rotors.
They also worked on harmonic oscillators with momentum flip.
Momentum flip. Okay. So momentum is not conserved in the bulk anymore. Okay. I don't know what. So your question is what would happen there?
Yeah. In this example, if you think about it, this would correspond to having one of the forces being not being of mean zero.
At the boundary scale.
Yeah.
I don't expect anything drastic to change. So, so for example, for the RTP, you then want so the rates from minus to plus and plus to minus would be different.
Yes.
That would give an average sigma there. I would still expect qualitatively it to be same. Abhishek, do you have any comment or any? Yeah, qualitatively, I would still expect it to be same because, yeah, but I mean, one can do the calculations.
Yeah. Yeah. And I guess the second question is kind of like what Anup did for his model, like the harmonic chains, but with momentum exchanges. Could we get like some kind of like hydrodynamic limit in this case?
Perhaps, I don't know.
Yeah. And it's like how much of like what you observed, especially on the boundaries, is like finite size effects versus things that survive as we make the system size larger?
You mean that whether we get the same behavior for a finite chain?
Yes, like what behavior survives as the chain gets larger?
No, so here, I mean, everything I discussed was in the thermodynamic limit.
Okay.
But I mean, the other question is, if you ask it whether, I mean, how much of it survives for a finite chain, the answer is everything.
Okay.
Yeah. But the expressions that I showed are all in the n going to infinity limit only.
Look, something like, for an RLL, that paper, like they said, like these like things that happen at the boundary decay exponentially fast with the system size, no?
Yes.
So would you not expect the same thing to happen here?
That's what you are seeing. Like, I mean, there is an exponential boundary layer if you look at the average temperature, but the bulk property is also decided by what happens at the boundary, right? I don't know if I answered your question.
Yeah, I think. Thank you.
Kabir?
Yeah.
Yeah, you were able to derive the exact distribution for the currents, but you also gave average current and that saddle point. What does the distribution tell you about the saddle point?
Distribution of the local current.
Yes. What is the, does it diverge at the saddle point? What happens there when it doesn't reverse sign anymore?
So as far as the distribution of the current goes, we could not see any specific signature in the shape of it, I mean, around the current reversal. We have looked. So even if we take a parameter where it's actually reversing the sign, the qualitative shape of the distribution remains same.
But what about, like, let's say the second moment, what happens to that near?
So second moment from here, I mean, from this distribution, we can calculate the second moment, which shows, I mean, there is no non-monotonicity there. And again, there is no special signature or special shape change around the current reversal.
So the saddle point is just for the average.
Yeah.
No questions, comments? Okay, so if not, let's thank Urna for a very nice talk.